Okay, basically, for chapter one, yeah. So these are all my details. You can find me on the science blog in the science blog as 216, and then my consultation hour is every Wednesday, Thursday, 3 to 5. Okay, and this is the assessment table. So for this course, for this module, we have 40 and 60. 40 for coursework component, 60 for the final. Right. So for coursework, we have one test, assignment, and lab. Right. Right. And all of these will be done online. So passing criteria, I still need to stress a little bit. So for passing criteria, so the first passing criteria is 50% of your coursework. Your marks must be more than 50%. Okay. So meaning if I add your test one, assignment, lab together, if your marks, and then I'll convert into 100%. So if your marks is less than 50 marks over 100, mean you will fail this module. All right. Or if after I convert everything into 40, you get 20 over 40, less than 20 over 40, you fail this module. Right? And then the final is passing mark is 30 over 100, mean the exam paper we mark 100 marks. We give you 100 marks, and then we see how you perform. If you score only less than 30 marks, then you fail the final. So then we will see the total marks for this module. Means we convert everything 40, 60, then we add up these two. So the final marks for this module, after we add 40%, 60%, if your marks less than 50, you also fail. So there are a few passing criteria here. You fail either one, you also fail. Okay. All right. So again, we only have 7 weeks to cover all these chapter. Normal semester we use for 14 weeks, 1/4. But for October semester we only have 1 week. So that's why in your table schedule it will a little bit. We spend more time together in these 7 weeks. Okay, this is the textbook that we are using. Right, now for chapter one, we cover only two things here. So when we look at 2D and 3D fluid field, and then we look at how we develop the equation of streamline. Okay, when you look at two, and then of course this module you make sure you understand introduction to fluid mechanics, because this module there's a prerequisite, means we assume that whatever covered in 3179 introduction to thermal to fluid mechanics means you already understand. All right. So in this module, if anything that relate to 3179, I will just pass. I will just maybe I will just mention a little bit, but I won't go deep into what already covered in 3179. Okay. Now, just now we mentioned that we have 2D and 3D. So normally in fluid mechanics, there is a word called kinematics of fluid motion. So on the slide here, you see there's a picture with this a 3D simulation that you see a sport F1 car, and then you see a white line here. All this white line here is called streamline, and then you'll see in a simulation. So if you've done your simulation in your final year projects, or later on you have some module that use simulation, you need to understand how all this line come into place, how the software develop all this. And fluid mechanics, this module will teach you on all these things, right? So when it comes to your final year projects, you should able to explain what are the lines to tell you. So kinematic fluid motion, we're going to look at velocity, acceleration, and visualization. So just now the equation of streamline is part of the visualization. And then using software to visualize our float motion, also one of the method. Okay. Now, of course, in okay, all these are visualization method. Just now you see is a line, streamline. This one is on the ball presentation. But still, if you connect all these ball, you still get the line. Okay. This one, another one. This one is a 2D representation. This one is in the ANSYS simulation. So yeah. So yeah. So for fluid mechanics, we'll look at these a few fluid properties. The first one, density. The second one, pressure. The third one, velocity and acceleration. So density, we use the symbol rho. Pressure, we use P. Velocity, we use the V. And then acceleration, we use A. So, yep. So these are the parameter or fluid properties that we are. These are the only a few examples. We have few more as we go deeper into other chapter. Okay, so these are the fluid properties, right? Now there's a blank there for question 2. So a few representation is a function of a partial coordinates. A few representation of the flow is a representation of fluid parameters as a function of partial spatial coordinates. So we're going to look at a few definition later on. So few representation, we are going to put into a function of their coordinates. So what are the parameters we're going to use to describe the fluid flow or the flow pattern? So we're going to use these two. So spatial coordinates or coordinates, we're going to refer to Cartesian plane x, y, z, or we have another coordinate, we call it radial, which is r, theta, and z also. But this is just an example if you refer as a function of coordinates. And then another one is function of time, t. So this partial spatial coordinates, this one refer to a space that our fluid contain. Coordinates x, y, z will tell you the space or working space. However, the time here tell you the location where our subject happen or our incident happen. So in the later chapter, you will see we always link these two main parameter together. So one, we talk about the space, or in chapter you hear about control volume. So this is about coordinate. Then the time is on the location at that particular defined time. All right. So one is space, one is location. So this one is on question 3 in your tutorial. So to describe a flow, we need a coordinate and also time. All right. Now, on your question 4 in your tutorial, you see the same diagram also. Now, let's look at the bottom axis first. So in X, Y, Z, this one is the principal axis, X direction, Y direction, and Z direction. And then you see if we have a vector or we have a direction, then we will use all this sign. If the component is moving along the x-axis, we use I hat for x direction and positive towards x direction. And then for your y, you use j hat for y direction component, and for the k, for the z axis, we use k hat. So this one you learn in your earlier other module or mathematics, calculus, and all this. So, or vector, chapter concerning vector. So this is a three-dimensional axis. And then another one is on another vector form. So you will see this diagram, you have a red color curve. So this one is on the path, we call it path, or how the fluid moving. And then the blue color arrow here with the V, capital V, this is our resultant velocity, which is our absolute velocity. All right, our velocity. So the velocity in this module is a vector. So vector means it have a direction and magnitude. So if you learn in the physics class, you know that your vector can transform into x-axis, y-axis, and z-axis. So your vector can transform into x-axis, y-axis, and z-axis. So if your velocity moving along x-axis, the magnitude, we call it u. We denote as a small u. Right? Small u represent vector in x-axis. And then your u also can break into y-axis, represented by a small v. V also a vector, but this vector, small v, represent a vector along y-axis. And then same with the w. W represent velocity in the z-axis. So you can write the equation of this you can define the velocity in mathematical way in this form. So if you want to define a velocity vector in the 3D space, mathematically you can write in this form. Okay, you can write in this form, v equal to u in the function of z, x, y, z, and t. So x, y, z is a spatial coordinates, and then t is a function of time. So time tell you the location. Right, coordinate the x, y, z tell you the space. T tell you the exact location at that particular time. Right, and then I hat plus v j hat plus w k hat. So in normal solution for our problems, usually we don't write all this out. We don't write x, y, z, t. We don't write this one out. Only when it comes to mathematic form or when you want to go deeper into derivation sometimes. So if you want to solve problem, you only need to write v equal to ui plus v j hat plus w k hat, like that. So this equation represent this vector in 3D dimension. Okay, right. Now what about if you see in your question 5, there's another representation of particles that flowing through times. So for example, in this example, you have x, y, and z axis again. And then, however, this one was present with r, with the radius or distance, radian coordinate. So with the r from origin, radius, and particle A travel from this point to another point. So here we will represent with the time t and plus delta t at second location. Right, so this particle move from here to here, and the red lines is particle path. All right. So RA is called a position vector. RA is called position vector. But in this case, it's relative to the origin in the reference coordinate, axis. All right. Now again, this is just a mathematic breakdown. So definition of velocity according to this diagram. For particle A move from one point to another point, we can write as this one. dr divided by dt means a change of r according to time. So dr over dt equal to velocity of our particle A. equal to VA. So this is how we represent or how we write our motion, our particle motion in mathematical form later on. So again, vector, velocity is a vector. So vector have a magnitude and direction. Right. So how we calculate the magnitude, this is just a recall in what you learned in your calculus. Yeah. So magnitude is you take the x component magnitude in x component square plus y magnitude square plus z magnitude square, and then you square root it, you get the magnitude. This is how we get the magnitude of your velocity. So meaning all this u, v, w, z is this one. U, v, w here. You square, 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 and then square root, you get magnitude. Okay. So this magnitude is for your question number 6 in your tutorial question. So yeah, question 6 asks you how to calculate the magnitude of the velocity if the velocity vector is given. So if you have a velocity vector, you're able to find the magnitude. Okay, now the next one, we're going to look at how we apply what we learned here. Right, so question 7 is application. And again, in your tutorial question there's a typo error. If you look carefully, the velocity field is V0 divided by L minus X. In your tutorial question there is J. So you have to change it to I hat. It's not J. It's a typo error there. So yeah, so yeah, be careful on the symbol that we use in calculation. Right, so make correction in your tutorial question there. It's not J, it's I hat. Where it tell you in this statement is V0 V0 is a constant, L is a constant. Right. Now what does this question 7 ask you to do? It asks you to find at what location the flow field is the speed equal to V0. This is the first assignment, right, of this question. And then we need to make a sketch of the velocity field for x more than 0 by drawing arrow represent the float velocity at a representative location. So this question actually is application of mathematics, just a revision of how you get all these things in mathematic form. So again, in exam, don't be scared by the equation, complex equation given. What you need to do is that you identify the velocity field, and then you know that identify whether this is a 2D problem or 3D problem. So if you have I, J, K, you have 3D problem, and if you only have I, J, means you have 2D problem. And if you only have one I hat or J hat or K hat, only have one, then you only have one-dimensional problem. Okay, now identify the velocity field first. So look at the component or dimensional dimension that you have in the question. All right. Then you know that you can break your equation, velocity equation, into U, V, and W. All right. You know that the velocity you can break into U, V, and W. And of course, you write the general form of a velocity first. So general form velocity given by V equal to Ui hat plus Vj hat plus Wk hat. So this is the general form. And then you compare this general form equation to the equation that given in the question. So in this question, we only have I and J. If the question asks you a bonus mark question, it asks you what is the magnitude of your Z component, means 0, because we don't have Z component here. Just give you a highlight. So just let you know. So automatically you can compare both equations. So you know that U equal to negative X V0 divided by L. So be careful on all these signs. Be careful in the exam, positive and negative. So remember to carry the negative sign when you derive or when you solve problems. Okay. And then V also you do the same. V equal to V0 divided by L times Y. This one is your V. We don't have W component. W component equal to 0. Okay, equal to 0 Z. Okay. So again, if you look at the component we have here, we don't have Z, so we only have 2D problem. Okay. So far, any question before we move on? Are you able to understand what we cover so far?
Yeah, understand.
Okay. Who else are in here? Joshua, is it? No, Vina. Vina is here. Okay. Vina, are you there? Okay, we move on. Okay. Right. Now, next one, we find our float speed or our velocity magnitude. So recall how we find our magnitude means you square each of the axis component and then we square root it. So again, recall this equation. So in the exam, if you write a general equation, you are given 1 mark. All right. So yeah. So this is how we access whether you understand to find magnitude of the vector or not. Even it look very simple, but it will carry some marks in the answer. So substitute what you find just now, your u and v, into this equation. Right? Substitute. So we have x squared plus y squared square root. So this is our magnitude for our float speed, for our velocity magnitude. So if you are good in mathematics, you're able to see the shape of the equation. So if not, then never mind. I will explain further in the next slides. Right? Because we need to, in this question, we need to scratch the velocity field for this equation. All right. Now again, we need to scratch the flow field. So you modify a little bit this equation, because we know that V0 and L equal to is a constant. This two is a constant. So you can move your constant value inside this equation. So V equal, yeah.
If make a sketch means we just write the equation.
You mean what? Again, your question?
If they are asking a make a sketch of the velocity, so
Yes.
we no need draw a diagram or what.
You need. Yeah, I'm going to show you the way, right?
Oh.
Yeah. So you rearrange this equation into equation form. So in your mathematics, you learn about linear equation, y equal to mx plus c. You learn about quadratic equation, parabolic, like that, or sometimes exponential, something like that. So you need to recall this shape, and sometimes the shape of the locus and all this. Right, so you rearrange this equation, the flow field equation that we have. Right, so we need to find at what location in the flow field the speed equal to V0. Mean this whole thing equal to V0. So what does this component equal to? Praka, what is this component equal to?
Magnitude.
Yeah, what is the value of this one?
1.
Yes, correct. The answer is 1. Right, because V0 times 1 equal to 1. So 1 equal to this component. Okay, we're going to scratch. We're going to scratch this flow field where the speed velocity equal to V0. So we're going to look at what shape of this equation gives us. So again, you're able to understand why this component equal to 1. is good. So you rearrange because this equation equal to 1. We arrange it so we get x squared plus y squared plus 0 equal to L. And then you move it again. You rearrange again. You get x squared plus y squared equal to L squared. Right? So I think you should be able to see the shape. If not, I'm going to show you also. So this is actually an equation of circle. So you recall the equation of circle give you x minus h squared plus y minus k squared equal to r squared. So what is h and k means? H and k is the origin of your circle from the axis. All right. So this is your h. This is your k. Okay. Right. And this one is your mathematics side. All right. Now you compare these two. You compare this equation and this equation. What is the origin of this equation, Prakan?
Origin.
Yeah. Where is your circle will land? Well, where is this center of circle? If you compare this one and this one, you compare this one and this one. What is the origin? What is your h and k?
H and K.
You compare these two. What is the value of h and k in these two equation?
1, 0.
How can you get one? Okay, you compare this one. I highlight on the screen. You compare this one and this one. What is the value of your h and k? How come you get one? Okay, I'll write again. X squared plus y squared. And then you have a general equation of a circle. X minus h squared plus y minus k squared. So what is the value of h and square here? H and k here. Compare these two.
0.
Yeah. So what is your origin now? Your h equal to 0.
0,
K equal,
0
so your circle at here.
at center.
Okay. Okay. So you know from this equation, you know that your flow field is at the center of your axis, and the flow field is in the circle shape. Huh? Okay. All right. Now you know that L is a constant value, right? And we need to make a scratch with the velocity field of x more than 0. Okay. All right. So you go into x and y axis. You draw x and y axis. And then you draw, and then because we're only interested in x more than 0, so we close the section on the left. So we're only interested to see what happened on the right hand space here. So just continue to draw. So you know that this is a circular shape. We can draw 1, 2 because each circle represents different r. Okay. So if the location at here equal to L, right? Because your R represent your L, right? So when you change the value of your constant value, you change the value of L, you get the location, the first location here, and then what happens if your x equal to 0, your y equal to 0, your x will be equal to L also, right? And you know that this is a Cartesian plane. You have positive and negative value. After the origin, you get negative, right? Yeah. Then you have 2L and so on. And then, yeah. So we know that if our L here, our X, if our L equal to, not L, if our Y equal to 0, Y equal to 0, so your X value will equal to X, your X value will equal to L. You substitute this one inside the equation. Substitute your X value into equation, you get value V0 here. Same, you represent, if you substitute your Y value 2L, you will get 2V0 here. Okay, so this is how we draft out our velocity field. Okay, and because our velocity have magnitude and direction, so we need to draw out the direction first. How we know the direction? How we know the direction?
Yeah. It, negative or positive.
Yes, correct. So again, recall the definition of a vector. So let's say you're given a vector. So you have x component, y component, and then there's a theta there. So you can define the angle of or direction of your vector with this equation. So tangent to, you take the opposite times the side, means you take v divided by u, you get the angle of that vector from the base, from the reference axis. So here we have u and v just now, u component and v component. So again, if we have want to define the tan theta, if you do the calculation, you have tan theta equal to y divided by x divided by x component. Okay, so we have this equation already. Then we can find the direction. Okay, draw the vector and then with the angle. So you can break your vector into x and y component. X component is denoted as u, y component as v, and then define how you find the tangent angle here. So in this case, if you substitute the given velocity field, you will get tan theta equal to negative y divided by x. Right? Now we substitute in the boundary condition. We look at x-axis as highlighted on the screen here. So along x-axis, our y equal to 0. Along x-axis, our y value along x-axis is 0. So our tan theta equal to 0 because 0 divided by something is 0. So tan theta equal to 0, your angle either 0 or 180 to get 0. So angle is either 0 or 180. Means it's either this way or another way, 180. The angle was measured from x-axis. Right. Then look at y-axis. So along y-axis, all the value in y-axis is x equal to 0. So when your x is 0, your value in this mathematical equation become infinity. So to have your tan theta equal to infinity, your angle must be 90 or 270. This one is in your trigonometry chapter in your mathematics. Okay. Right. recall the general equation we have, velocity field. So along x-axis, which is here, and then you look at your velocity field, you know that your y equal to 0. So this equation, this component equal to 0. And your x have a negative. All right. So the equation at the end, the magnitude of your velocity is negative v0 divided by L, and is in the direction into the origin, like what we show you on the screen here. This one is for the first one, v0. If you do the calculation, you can do for the same on the 2v0 also. So the direction is go inside because the original condition is negative.
So
Mm.
if the negative x is in x-axis, right?
Yeah,
If a negative is it will be a left-hand side, right?
again.
If got x-axis of the x point is negative,
Mm-hmm.
the coordinate it will be at the left-hand side, right?
Okay. Our axis always look like this. All the
Yeah.
positive are always to the right. All
Okay.
the
Okay.
positive will always like this.
Okay.
So you compare the original one with the equation. So if you get a negative, means you go to the opposite direction. No?
Okay.
Understand? Because you look at your view, your u vector here. You have a negative, right?
Yeah.
It means what? It means it go against the reference direction, because all the positive value is in this direction. All the positive will be go
Yeah.
to direction. So you get negative means you go to another direction.
Okay.
Uh, okay, right. Then we look at y. So y-axis, when your x equal to 0, again look at the velocity field again. If your x equal to 0, we don't have this component. Take out. Then you only have the positive value of your y with the constant value v0 divided by L. And then you have a velocity vector tell you the direction. Positive means it go up. Right? So in your diagram, you draw the direction of your flow field and y-axis. Right? You do the same for 2L coordinate also, you'll get the same direction. Okay, we have done for the axis, the major axis. What about here? What about center of this curve? What about the direction? And of course, the rest, if you do the calculation, you can do for the y-axis also. Y-axis is in another direction. Okay. Because your L is negative, you substitute inside this equation, you get negative. All right, so we're done for the y-axis already. Our next question is more on the direction in what happened to this point and this point. Where and also this point also. How the flow either flow up or flow down. How you determine that? Okay, we're going to look at that. Right, at 45 degree. So again, you look at the general definition of your vector at 45 degree. So this is what we defined just now. Theta equal to arctan of your v divided by u. So here, 45 degree. Okay. So at 45 degree, if you draw a mathematic form, you know that if you have a 45 degree line, your y equal to x. This line will always y equal to x if you have a 45 degree. All right. Now this is also very basic in mathematics. All right. So this one cover in the linear equation, graph for the linear equation. These are the concept that you need to recall back. Okay. All right. Now, right. So it's 45, your y equal, all right. So along x and y, along this line, y equal to x, means in the equation of your tangent equation, tangent theta equal to y divided by negative x. So if you want to look at what happens along this line, so tan theta equal to -1. Tan theta equal to -1. All right. So you let your x equal to y equal to 1. Your velocity field will be like this. So you redraw, let's say you do not know the direction, you just draw out what is this equation. You look at the x component first. So this is the x component, it's a negative, so you go to the left hand side. And then you combine with the y direction, this one, y equal to v0 divided by L times your j. Right? We assume our x value is 1. We assume our x and y value equal to 1. So you get this one and this one. So you combine these two vectors, you get a resultant vector, right? In the vector chapter, you get a resultant vector, right? You get this direction. So you can transfer what you understand from this equation into this diagram. So when the line is 45 degree, the vector direction is in this direction. It's going uphill. It's going uphill rather than going downhill. It's going uphill. If you substitute all the boundary condition, x equal to 1, y equal to 1 at 45 degree. And then you do the same for the 2L line location here. You also get the same.
If a tangent got a positive means it's going down.
No. Okay. You don't confuse with the positive and negative. Okay, let me revise the mathematics first. All right. Now, you understand why we get this line, not why we want so interest to get 45 degree.
Okay.
Yeah. So to get 45 degree line, to get this line was given y equal to x.
Yeah. Okay.
Okay, y equal to x. And the value along this line for our tangent theta is -1. So this is at this moment, this value do not tell you anything, but when you solve complex problem, it means something else. So at this moment, you just know that the tangent value equal to -1 if you substitute x and y in this equation.
Oh, okay. If
Okay.
tangent y over x exists, negative x means the tangent is -1.
Yes, because we refer to this vector diagram.
Okay.
And how we get x and y negative, how we get -1 because the u and v value we get from this equation earlier.
Okay.
Understand?
Okay.
So when we start substitute what mean by u and v just now, you simplify the equation, then you will get -y divided by x. You still remember what is mean by u and v? This one. We substitute. We extract from this equation. This is what we explained just now. How we get our u and v. So you do the calculation for tangent, right? Then you'll get -1 here, right? And then after that, you substitute. You assume you let x equal to 1, y equal to 1 in this equation. then you want to, because here you can substitute any constant value, because we only want to see the direction of the vector. So that's why 1 is a very simple value. So we can simplify this equation in the more simpler form. So when we substitute x and y in this direction, so this is 1, this is 1. So we will get our x component like that. We know that our x direction is going left. And then you look at another component in y, we know that it's going up because it's positive, like that. Then we know that our v here is our resultant. Resultant is a combination of two components, x and y in this component. So you always start with the origin, and then you combine origin to the endpoint of your vector. So that's why you get a resultant v like that. So here we know that along this line, the vector will always look like that. Along this line. Okay. By referring to this diagram. Okay. So that's why we can draw like that. Okay. What about then another one? Yeah, any question?
For example, if this question is like just two dimension question, if we got a 3 dimension plus
Okay.
W means
Yeah, 3 dimension is more complex, where you can no longer use this diagram anymore. You need to plot in a 3D form, meaning you have this 3 Cartesian plane, and then you need to look at x, y, and z component magnitude. You plot accordingly to the magnitude here. So it's a 3 coordinate. If you have a 3 component, you have a vector with I, j, and k. You have to plot inside the 3 Cartesian plane. So how to plot this one? You need to refer to your advanced mathematics on the 3-dimensional plotting, how you plot all these coordinates. Okay, so in this case, we look at 2D. We only have x and y. All right. Now, what about negative 45? Negative 45, we know that y equal to minus x, because y equal to mx plus c. We know that this one is the intersection at origin, so c equal to 0. So m is our gradient, so negative is this direction, right? Yep. So this more on a revisit on the mathematics side. So again, if you substitute the equation, you repeat the same equation, you get this direction, because your vector go like this, and your y go like that, and your resultant vector will go like that. Okay, u and v for 45 degree. Okay, y equal to x, negative x. All right, so this is how we get. So yeah, another question is that just to think about what happened at the origin here. What happened to your flow at the origin? So you just substitute the boundary condition where x equal to 0, y equal to 0 into this original velocity field. So when x equal to 0, y equal to 0, the total velocity here is 0. All right. So we use a technical word called stagnation point. So if for this module, if you see the word stagnation point, it means there's no flow in that particular location. Okay, when your x, in this case, when your x at origin, y at origin, with x equal to 0, y equal to origin, your total velocity will equal 0. Even these two are the constant value, but constant value times 0, you get 0. So it means there's no flow in the origin, at the origin. Okay. So application of this velocity field will be if you're able to stretch out the field, the flow field direction and magnitude, it will be application on simulating what happened to a flow hitting a billboard. So flow from the right and then hit the billboard. The velocity will go along the x-axis and then turn 45 degree and then flow along y-axis for x more than 0. So this is a explanation how you get the simulation result from the software for any flow software, flow analysis software. This is the fundamental understanding on how you get the representation or visualization on the graphic, on the software graphic interface. So when the time you present come to next year, your final year, if you, I think most of the time you will handle software, so you need to understand all these concepts. If you're not able to understand, explain how you simulate things, then it's going to be big problems during your presentation. Okay, we have done for the question 7. Yeah. All right. I think we go for a short break. Is that all right?
Yeah, sure. Thank you.
Okay, I stopped the recording for a while.